Hello, in this video we're going to talk about some of the applications of the inverse function theorem. What we proved last time is theorem 4.11, which says if you take an interval and you have a function from that interval to r and your function is strictly monotone, then the inverse of this function is continuous. So every function that you take, as long as the domain is an interval and the function is strictly monotone, either strictly increasing or strictly decreasing, the inverse of this function would be continuous. So this is very interesting because it doesn't even require your initial function f to be continuous. All it needs is for the function to be strictly increasing, because otherwise it would not have a or at least it may not have an inverse, and also the domain to be an interval. So these are the two conditions we need. Let's look at an example and then we'll see how that relates to rational exponents. For every positive integer n, the function f from 0 infinity closed 0 to open infinity to r given by f of x equals x to the n is strictly increasing. Okay, so this part of it the first part is one of the properties of inequalities. So if I have x less than y greater than or equal to 0 and I raise both sides of this inequality to a positive integer exponent, then I have x to the n is greater than less than x to the y to the n, and this means f is strictly increasing. So that's clear. Therefore its inverse is continuous, and that's also pretty clear. So this follows from the theorem (4.11), because this is a strictly increasing function, its domain is an interval, therefore its inverse would be continuous. Now, what is the inverse of x squared? It is square root of x. What is the inverse of x cubed? It is cube root of x. So this is why this example is important, because it tells us that nth root of a number, the function that sends every x to nth root of x, is a continuous function. And of course you need x to be positive, because there could be issues when n is even. Okay, so this brings me to definition 4.1. Given a rational number r equals m over n with m and n integers and n positive, and a positive number x, we define x to the power of r as x to the power of m to the power of 1 over n. And x to the power of 1 over n is the inverse of x to the power of n. If the exponent is non-zero, we define 0 to the power of r as 0 if the exponent is non-zero. Now, and a notation that is common is x to the power of 1 over n is denoted by nth root of x. Now, one thing before I can move on and look at one of the main theorems that I'll do today, which is to say x to the power of rationals is a continuous function, and also look at some properties of exponents. Notice that this definition depends on the way you write down your rational number. In other words, if my rational number is, let's say, 2/3, I could also write down this rational number as 10 over 15. But the way the definition is given is it is given in two different ways. One way is x squared to the power of 1/3, and the other way is x to the 10th to the power of 1 over 15. So these are both given as the definition of the same thing. So therefore we need to make sure that these two are in fact the same. Okay, so in order for these to be the same, we need x squared to the 1/3 to be the same as x to the 10th to be to the 1 over 15. Now, when are these two equal? X squared to the 1/3 is equal to x to the 10th to the 1 over 15 if and only if, so if I take a look at this number to the power of 1 over 15 is equal to this number if and only if when I take the 15th, when I raise this to the power of 15, when I raise x squared to the 1/3 to the power of 15, that by definition of inverse function, that is equal to x to the 10th. So these two are the same if and only if the left are the same if and only if the right are the same. Now, let's look at what happens on this side. If you have something raised to the power of 15, you can write it down as raised to the power of 3 and then raised to the power of 5th. So those properties of exponents are things that are easy for integer exponents. You can prove those by induction, and in fact I have proved these as examples in the earlier section. This is in chapter 0. So I can write down x to the power of 2/3 to the power of 1 over 3 to the power of 15 as this to the power of 3 raised to the power of 5. So these two are the same if and only if these two are the same. However, since x to the power of 1/3 and cubed are inverses of each other, the left side is x squared. So x squared to the power of 5th is equal to x to the power of 10th. And of course, this is valid. Of course, x to the power of x squared to the power of 5th is equal to x to the power of 10th. In other words, if I have two different representations of the same rational number, I would get the same definition. I'm not going to get two different definitions. So in order to prove that, and this would be something pretty easy, so I'm going to leave that as an exercise. So what you want to do is you want to write down m as n, r as m over n, and also write it down in a different form, a over b, where m, n, a, and b are integers, and n and n are positive. Then we need to prove that, in fact, x to the power of m to the power of 1 over n is the same as x to the power of a to the power of 1 over b. And the way you want to prove this is by using the definition of what it means to be what it means for what's the definition of the 1 over n raised to the power of 1 over n, which is the inverse of inverse function of x to the power of n. So just basically raise both sides of this to the power of nb and then show that those are the same. Okay, so there's some stuff that needs to be done here, but pretty similar to what we did, pretty similar to the example that we did. Okay, so now that we know how to define real numbers raised to the power of rational numbers under some constraint, your base cannot be negative. We can talk about some properties of exponents. So if you take two rational numbers r and s, and then non-negative real numbers x and y, then we have x to the r times x to the s equals x to the r plus s. We do need some conditions on r and s, so perhaps it would be best to say x and y are positive. Just because if you have a base that is 0, you cannot raise it to the power of 0 or negative exponents. So it's best to change this to positive to make sure we don't have to take care of the cases where an r and s are 0 or negative. Okay, so let's prove this one. I'm going to prove one of them, and then the others are actually quite similar. So let r be m over n and s be a over b, with m, n, a, b be integers and n and b be positive. Now these two are the same. X to the power of r times x to the power of s is the same as x to the power of r plus s if and only if, so I'm going to write down the definition. X to the power of r is x to the power of m to the power of 1 over n, and x to the power of s is x to the power of a to the power of 1 over b is the same as x to the power of, and we just take the common denominator, we get mb plus na, and that raised to the power of 1 over mb. So all I did was I used the definition of x to the power of r, and definition of x to the power of s, and definition of x to the power of r plus s. Okay, now these two are the same if and only if this guy is the same as this raised to the power of mb. In other words, because I know raising to the power of mb is a one-to-one function, I can raise both sides to the power of mb. So x to the power of m to the power of 1 over n, and I'm making sure that all of the steps that I'm writing can be reversed, because in and this is gonna be nb, not mb, because what I'm trying to prove is I'm trying to prove this one. So I cannot assume this equality. I have to prove it. But what I'm going to do is I'm going to make sure that every step that I'm writing is reversible. Okay, so this raised to the power of nb is equal to x to the power of mb plus na. Now, again, I know the properties of exponents for integer exponents. So I can break it up as this to the power of nb times that to the power of nb. So this is x to the power of m to the power of 1 over n to the power of nb times x to the power of a to the power of 1 over b to the power of nb. And that's equal to x to the power of mb plus na. And as I emphasize, we do not know these equalities. We are trying to prove these equalities. So we are not assuming these equalities. Now, again, I'm going to use properties of exponents for integer exponents. I'm going to write it down as 1 over n raised to the power of n, and that raised to the power of b, or yeah, and the other one is x to the power of a raised to the power of 1 over b raised to the power of b raised to the power of n, and that's equal to x to the power of mb plus na. These are equivalent. Now these two are inverses of each other, so that means this becomes x to the power of m to the power of b, and 1 over b and b are also inverses of each other. These are inverse functions, so that means x to the power of a to the power of n is what we get. And of course this follows from properties of exponents. But this is only when exponents are integers. Okay, so this proves one of these equalities, x to the power of r times x to the power of s equals x to the power of r plus s. The other two are very similar to this equality. Okay, so finally the main theorem for today is that if you look at x to the power of r, you get a continuous function. If you take a rational number and you look at f of x equals x to the power of r, that would become a continuous function. If your r is positive, then you can also include 0, because then you won't have any issues with having a denominator of 0 or 0 to the power of 0. If you take those functions, those are also continuous. And the reason is, if you look at the first one, the reason is this function is a composition of two functions. So look at f of x equals x to the power of r. So if you write down r as a ratio of two integers, let r be m over n with m and n integers and n positive. Then x to the power of r becomes x to the power of m to the power of 1 over n. So what we know is this. We know that x to the power of m is continuous over the entire real line. We also know x to the power of 1 over n is continuous by example, I guess I talked about that at the very beginning. That is example 4.42. By example 4.42. Therefore, by a theorem, their composition f of x equals x to the power of m to the power of 1 over n is also continuous. And that's exactly what we wanted to show. And the other part is also similar, the part about when r is positive, because the only obstacle is the x to the m being continuous. And x to the m is continuous because when r is positive, m is also positive, and x to the m is always continuous as long as you do not have 0 in the denominator. And since m is positive, there's not going to be any denominators. Okay, so we will continue with this next time, and if you want to continue with this topic, feel free to subscribe, and I will see you in the next video.